Hello, and welcome back to Old School Coding. I've been doing a little bit of touching up between sessions. You'll notice that in the upper left hand we have a slightly improved display for the benchmarking, which it's moving towards something that I can automatically parse and do some analytics on later on as we get more and more benchmark numbers. The important things are still there. I have reduced the precision of the output because there is variability in the benchmarks, and there's no point in listing the lapse time to a nanosecond or actually to a picosecond, which is what I was doing, when it can vary by a nanosecond on each call. So now, with these printing to the 10th of a nanosecond for the elapsed times, I'm seeing that they still vary a little bit, but not wildly. And as I run this command inside Emacs, it's not recompiling. It's fetching the logs of the most recent recompile, but it is rerunning the benchmarks. And we can repeatedly hit G, and I can see these numbers staying stable or getting bigger or smaller. Down the lower left, that window, I'll use it for notes and such. Not really interesting for the video, so that's where I'll put my picture, because I've had feedback that says, hey, not bad seeing your face. So we have all of these packages that we have set up so far. All of them are under the hood kinds of things for this particular simulation engine. Notice that I called something FIFO. It's a very specific FIFO. It is likely that for this program, it's be my only actual use of a FIFO. And if it isn't, then I may need to rename it, or I may need to put a comment out there in the code that says, okay, we're calling this FIFO because it's a FIFO of steps to run. And that's a very specific thing. And if I've got a FIFO of something else, I will give it a longer name because it's nowhere near as important as the fundamental FIFO of things to run. Anyway, our task for today is to work on the first of the actual packages that looks like a simulation. So the core of a simulation of an older computer system is going to have to be, if you're doing, signal level things, the idea of a wire with a control signal on it that can go up and down and allow functions to notice. So when a particular signal has a rising edge, there's logic I want to run. And when it has a falling edge, there's logic I want to run. So I am centering around a data structure called an edge, which will actually contains more than just one edge. It represents a control signal in the simulation. It has a value, which is going to be normally 0 or 1. We will maybe think about extending that in the future to include things like tri-state, or maybe it's got multiple bits, or who knows what we'll do in the future. But for now, it's a single bit. It has a current state. It has a list of subscribers to call when that state goes from 0 to 1, and a list of subscribers to call when that state goes from 1 to 0. It has a way of calling in and saying, please set your state to 1, or please set your state to 0, or please set your state to this value, which we will allow as a convenience. So you can say, I'm going to do this Boolean expression and put the result of it on the signal and have the signal do nothing. If the signal doesn't change, it's not going to notify any people waiting on edges because there's no edge. Also, because I want to catch certain kinds of bugs in the simulation, which are actually simulation configuration errors, I'm going to carry the time at which we last had an edge. So it will store a tau. And what I'm going to do with this is, if you have a rising edge, we're going to store the tau. If you have a falling edge, we're going to store the tau. But before we do, say, well, how long has it been since our last rising edge? If we have a rising edge and a falling edge on one control signal at exactly the same tau, I'm going to send out a message, because that's bad. that indicates a hazard. For example, if you're implementing an AND gate and you've got two inputs to the AND gate and you're listening to both of them as edges and one of them is high and one of them is low, like that, and you rise this one and then you fall this one. If these happen at the same time, that's called a hazard. And in electronic design, you recognize that and you say, wait a minute, this means my output, these two signals were never really high for any length of time together. So my output should stay low. But if we see the rising edge of one first, we're going to blip our output high and then we're going to blip it low. So our output then, the behavior of our output would depend on what order our inputs were updated. And if both edges of the inputs are coming in at the same time, that's undefined. So I am going to make this message that happens if you try to have a rising edge and a falling edge at the same tau. I'm going to emit a message that says possible signal hazard. And we're going to stop the simulation right there because that's an error, like I said, in the configuration of the simulation. You have designed a piece of electronics that will have weird behavior, or at least it will have behavior that we cannot consistently simulate in this simulation. Maybe it's okay. I mean, plenty of people have hooked up the output of an inverter to its input and made an oscillator, especially if you add a cap and a resistor. But that does indicate a situation we won't simulate. So there we have it. Our edge has a value. It has a time, a tau at which the value changed. It has a list of rising edge subscribers and a list of falling edge subscribers, and that is enough for us to get going on building it. So edge.c and edge.h. Oops. So there are some things we need out of all of our packages. I'm just going to go ahead and type them. They are post and bist and bench. Extern void. This is edge underscore post. Bist and bench. And I think I'm going to start moving away from using those big comment blocks that say this is the support for this and this is the support for that, at least during the live coding, because I can't type them real fast. What I will do is I will probably insert those blocks between sessions as part of the tidy up. But for now, we're just going to do this. And let's put in print top and print end so we can notice that these are being called. I'll remove these once we have verified they're being called. And then we have our basic starting point for all of our packages. Now, currently, that's not triggering. Oh, it is. Okay, so we did manage to get it to recompile. And it says, oh, we've got that problem. So include support.h. And there we go. Implicit declaration of print top and print end. In here, okay, so let's see here what is going on. Did I misspell them? Oh, print top and print end. They're here in support.h. Okay, I got an old log. What happened was I didn't wait long enough before updating my Emacs compilation. I should have paused for just a second and waited until my other window showed that the compile had completed. If I save this too quickly, it will confuse things. So we're going, and it's not running them yet, so we need to go into main.c. Main.c is a little bit updated. I modified the main program so that now when we run our bist, we divert to main bist, and it gets the rest of the argument list, and in the future, we will be able to use the command line parameters to select which tests to run. That's coming in the future. We're still fast enough. We still run all the tests in such a short time that it just doesn't matter yet. So wherever we have sched, I'm going to add edge. just like that. And now, when I look at my log output, I see that the output logs now differ, saying that post and bist are being called. Oh no! And bench isn't being called yet because we don't run bench unless everything else passes. And apparently comparing the output files is something that has to pass. But I can explicitly ask for bench here. There we go. So I'm going to run bench and then logs and then format. I actually don't need to run format here. Our standard thing that we do over on the other window, our standard build loop that's running in the background at all times, now includes running benchmarks and reformatting the code. So if I do a save from the editor, it will be noticed, and we will compile it and run it. And if the post and the bist pass, then it will automatically get reformatted, and Emacs is set up to reload from disk when the disk updates. So if I, for instance, extent that line, I do a save, it's going to do stuff, and boom, there we go. So we now have automatic reformatting inside Emacs. Yes, I used to do this as I worked. So yeah, I'm going to make a point of calling out anything I do that I didn't do back in the early 90s as a more modern thing. For example, Git didn't exist then. Branches to the source code control system were crufty and hard to use, so I was less flagrant about using branches. So currently what I'm doing with Git is I'm doing most of my stuff trunk-based. I will occasionally build another branch. I did a branch recently for something. I did a feature branch, and that ended up just turning into trunk. There was no real point in doing a feature branch at that point. I was thinking about it. But anyway, so using Git as if it were SCCS. I have flashbacks just saying SCCS, I'm sorry. So now, when we run our bench and logs, this is saying, here we are. Oh, I ran it while the other one was running. So we have top edge post, end edge post. Then we have the standard error output from our benchmarking. Standard output is buffered. Oh, no. Okay, so this is the standard error output from the other benchmarks. That's cool. And this is all standard error. So I was going to talk about how standard output would be buffered and might, if you printed something as standard out and then standard error, the line to standard out might appear later, but that isn't occurring here. So we do edge post to get that done. We run all of our other benchmarks, and we come back and we run our edge benchmark here, which is currently doing nothing. So now to make it so that our compile is succeeding, I'm going to go into logs, and I'm going to delete the expected output guy, and that will get rebuilt the next time we trigger a build. And now difference is 0. And now if we rerun our bench logs here, that's what we get. So now we're hooked up. So as we make changes to post, bist, and bench over here, they will be reflected in our build because we know we're running them. Actually, we know we're running post and bist, and we know we're running the bench because there it is. So I think at this point I am safe to remove those macros, and I'm going to have to go back and hit that log file again. And really touching anything will trigger my build. The build does not trigger if you remove something. That's for a very simple reason. If I said, it does a build and then it waits. If I said stop waiting if something is missing, then the build would basically spin infinitely fast, well, repeatedly over and over again without delay, if building that something failed. So we try to build the executable, and if it isn't built, if there's a linkage error, it won't exist. And we get down to the bottom. If we waited and we said, well, stop waiting if the executable goes away, boom, we're in infinite loop. So what I do is at the bottom of the build, I look at the files that were the source files involved in the build at the time. Or actually, I look at the source files that I would use right now to do the build. And I wait until one of them is modified or deleted. So if we delete a C file, it'll rebuild. If we add a C file, it won't rebuild until I do something to include in the build. That makes sense because just tossing foo.c into the project doesn't impact the project until something calls it. But I have to modify existing C code to call into the new thing. Although any build that you do, for any build you do triggered anyway, will bring in the new .c files. So it isn't strictly only building the C files that are being called. It's just not waiting on them. There we have it. Okay, so what is an edge? Let's get into our edge header here, and let's start defining it. We have a struct here. I'm going to start naming my structs, giving struct tags, because the debugger and the compiler talk about struct unnamed because it doesn't have a struct tag, even though I'm using a type def. So this is p-edge, and edge is up 1. And I'm going to use the original form of the struct tags where I use actually it's just as, no, let's not. I'll use s-edge. So struct s whatever. And the structure is empty. The compiler actually warned about that. We'll see that here in a moment. Yeah, there we go. Yeah, and we are doing our bench. We're building bench here before we're building logs. Let's do it the other way around. So there we go. And our first warning is the structure has no members. Yeah, okay. But I'm thinking that to make my debugging life a little bit easier, I'm going to take a bit of a yak shaving tour here, and we're going to go give structure tags to all the existing structures. So get, and we're going to say grep minus w, so it's going to be looking for the entire word, and we're going to n to get the line numbers, and f, and we're going to say struct star.h star.c. Struct s edge, this is going to be struct s fifo, and struct s sched, and struct s step. That also means that if I wanted to build an array of 10 steps, I could use struct sStep to do it. Not that I will, but it's there if I need it. Time spec is provided by the system. Again, I'm using the array of 1 trick so that I don't have to explicitly remember to take the address of TP all over the place. This arrow, yeah, TP looks like a pointer. It's an array, so it's the name of an array, so it decays to a pointer on use. But this doesn't actually take any longer than declaring TP without the array and saying TP dot. It's literally the same output. srep ctx, and that's all of them. And now if we go back to our build, we're back to where we are. So we have made our life a little bit easier with a small digression. So what does edge contain? What was I saying it contained before? It contains a value. So we're going to say bit value. And we're going to contain a tau for when it last changed. And we want a subs for the rising edge, and a subs for the falling edge. Now, as we work on edge, I'm not going to open the source code for subs, not unless I need to change subs, okay? I'm going to work based on the public interface because we are not subs. We don't want to tangle the internals of edge with the internals of subs. This is an ongoing thread in a lot of software engineering discussions, and every few years somebody talks about it like it's a new thing. I remember people talking about not tangling the implementations of your subroutines when I was working in Fortran in 1978. Okay, so that's how long that's been around. It's okay that people think that they've invented something new. It really is. I don't mind that. But I do want to mention that if you're seeing me use it, it's something I did back then. So I have a bit that's a value. I have a tau for last change. I have a rise and a fall. I'm going to do one other thing. I'm going to say bit busy. Along with last change, I'm going to say that in order to keep the simulation itself from doing an infinite recursion and blowing its stack, I'm going to say when I am evaluating this edge, when I'm changing the value and setting last change and evaluating all of the rises and all the falls, I'm going to set the busy bit in the edge. So if I do a rise and I call a bunch of things, which calls a bunch of things, which calls a bunch of things, and one of them tries to do a fall while I am processing the rise, that's an immediate fail, an immediate assertion failure. So busy is not a multi-thread lock, okay? It is a protection against infinite recursion, and we're going to catch the infinite recursion the moment we close that loop. So there's our values. So we save, and I'm going to do this, and it says, oh, I don't have a thing called bit. Okay, so now we start getting into simulation-specific stuff. This is not a type that goes in support, because this is a representation of data on the simulated host, not on the simulation host. So the simulated, I'll call it the target. So this is a target bit. So we're going to open up a file called target.h, which is going to be, it's going to be definitions that talk about the system that we are simulating. So if I'm building an 8080 based system, it'll be one set of things in target. If I'm building a Spark system, it will be a slightly different list of things because the word and the pointer are different sizes. If I'm building a simulation of a 64-bit AMD, whatever the latest thing is, it'll be at a different set of things. But this is for the 8080. Definitions for data types to use in the current simulation target, not some kind of 8080 based microcomputer that would have been sane in 1985. How about the late 80s through early 90s? Now, late 80s through early 90s, well, 8080, the documentation I'm working from is from 1975. 8080 was a common thing to see kicking around in 1980. By the mid-80s, mostly you saw 8085s and Z80s. And that's about when you started seeing the 16-bit CPUs. But a lot of people still had these 8080-based machines. So I think it's fair to say sane in late 80s through early 90s. By then, people were getting very, very good at building microcomputers around the 8080. There was a lot of good support chips. There was a lot of good technical knowledge spread among the engineers. So that's the kind of system we're looking at. So what do we need? Type def bit. Bit needs to be unsigned char bit. Now, more to the point, I'm going to use a data type defined by the C standard called uint8. We're going to go over to here, and I'm going to pound include target.h. So edge is the first of our simulation modules that will be target specific. So uint8 underscore t should have come from C type. So we're pound include headers.h. There we go. Now tau support.h. Now, as I reformat things, it does reorder the includes. So don't worry about the order of the includes. They're going to be forced on us. We have a subs. It's in here like that, and that now compiles. And you notice it reordered the includes to be in alphabetical order. If I included any system includes, my inclusion thingy would have bubbled them up to the top and sorted them. So what else do we need? We need a byte. Okay, the reason why I did a bit as a UIT 8, C does provide for single bit storage inside a structure. And that's cool, but you can't pass an address of a single bit on any host that you're likely to have today. Most of our machines have memory that is byte addressable. It's not bit addressable, but it is byte. There were machines back in the day that were not byte addressable. You loaded memory and stored memory in words. So we thankfully do not have to deal with them. And for the 8080, a word on the 8080 is 16 bits. And that will forever live on in Microsoft Windows because they are stuck in the idea of a word being 16 bits forever. So they have dword. I don't know what's happened with their data type since then. I disagree with so many things Microsoft did that I just don't keep track anymore. So bit, byte, and word for the 8080. So here we go. We've got a bit value. We've got a tau last change. We've got a rise and a fall. And busy isn't representing anything in the target system. So really what I want to do is just say int busy. So I just need something that's convenient for the host to set, clear, and test. So I just noticed a weird thing in my automatic build. If I write one file and trigger the build, if I write a second file while that loop is running, it doesn't rebuild in the second file. So I am considering shoving in a delay into that build. I hate to delay. Yeah, I think what I'm going to do is I'm going to take the benchmark. Yeah. So I need build wait to run quickly, which means I need to have build wait not do bench and format. And in fact, I'm going to not print the logs. I'm just going to do this. So build wait is now dead simple. So in my little window that you're not seeing on the screen, it's off to the right. It's just going to repeatedly do this make loop, which is as fast as possible, make what I want to make inside the loop. And we won't do the logs and such unless we're over here. That will speed our build so that if I'm writing multiple files, things work. The other thing I want to do is insert a small sleep here. So if we have multiple files being written, we're going to give it a second. We're going to see the previous one, the make wait that we ran on the previous iteration is going to terminate as long, the moment it sees any file update at all. We're going to give it a second for any other files to update that I'm writing. So if I'm in the editor and I do Control-X-S that modifies all the things, rewrites all the things, that should complete. So there we go. So we're going to wait 1 second after we see a file update and we're going to start the build. And I could probably change that to 5 seconds. Because I do not need things to happen every second. 2, 3, 4, 5. That feels too long. Yeah, 2 seconds. Yeah, 2 seconds seems to be about right. But I do have to wait those 2 seconds before I reach over here and display the logs and the benchmark results. That should help with our race for multiple file updates. And yeah, this squirreling out to do other things while you're developing pieces of code is so 1990. This is nothing that it will ever change because software engineers have a yak shaving problem. And look that up if you've never heard about it. It's an amusing story, but I cannot tell it well. Basically, it's you're working on something and it doesn't work because something else needs to happen first. So you go work on this prerequisite job. And it's got a prerequisite. It's got a prerequisite. Think about a badly designed role-playing game, computer game, where person A wants you to do something for them. You get something from person B, and person B says you can have it, but first you have to get something from person C. Person C says you can have it, but first you need to get something from person D, and so on down the line. This is the yak shaving problem, where you're engineering something and it depends on something you haven't built yet. So you go start building the new thing. And you're engineering the new thing and it depends on something you haven't built yet. So you go build the new thing too, and so on. This is why I feel free to dive out and do things like define bit. Okay, so there we have it. Another point I want to bring up that just occurred to me is we are defining our structures in our main header files. So anybody that includes our header file not only gets our public API, post, bist, bench, add, subtract, delete, run, etc., they also know the exact layout. And this is a weakness of C, is that you cannot have elements of the structure. Well, C is really weak because I can't mark any of these private. So I can't even tell the compiler, hey, don't let somebody outside my class access my class members. But there's a weakness of C and C++. I should be able to say, this is a structure called edge. I'm going to define it privately over in this stuff over here. But publicly, you still need to know how big it is so you can declare them and build one statically. Rather than calling malloc or new, you want to say this is a foo, and it allocates enough storage for foo right there and initializes it. So we need to disclose the contents of the structure in the header file so that when we're compiling the guys that use it, they know how much memory to allocate when I say edge X. And it's this guy right here. I could do my entire API using pointers, but that means that we would be doing a lot of trips to memory. So we have a pointer to this, and it contains a pointer to that, and it contains a pointer to the others. Chained pointers are a really bad thing because they blow your pipeline in your CPU. Your CPU wants to be able to queue up, read this, read that, read the other, do this thing, and store it there. It wants to have all that information up ahead, but it can't queue up the second read until the first read completes. So you do the first read, and then you can't do anything more. You have to wait. The CPU sits there idling, waiting for data to come from memory. Oh, it's so painful. A lot of my early optimization work that I did was to eliminate that kind of thing, eliminate these chained accesses through memory, and this is one of the tools. So that's why all of this has to be available to everybody calling. So basically, I could put a comment here that says, hey, callers, please do not access these important internal things. That's basically the C paradigm is you give somebody a souped-up supercar with no seat belts. And if somebody wants to use a seatbelt, they can, but it's up to them. So basically, this is how you mark something private in C. So let's get to implementing. So we need an init. We really put that down at the bottom. Extern void edge, init of edge. So we've got an init function now. So we need to initialize all the stars. So we could be passed in an edge that's sitting on somebody's stack. It's literally got garbage in all the bits. So e arrow value equals 0. E arrow last change equals tau. So whatever the value of tau is, we're going to store in edge init. Actually, we want tau minus 1. So we want to be able to change the value of the edge at the same tau as we were when we initialized. And I already have a compile error. Tau undeclared. Who owns tau? So, let's see, it looks like stepat owns tau. kind of obscure that step_at owns tau, but the reason why it does is step_at says this is a task, a function, to be executed with this parameter at a given time. So when we run one of those, that sets the simulated time to the time of the step_at and then runs it. So it is the sole source of tau. Other people will indirectly specify tau by saying when you call this service, it happens at this simulation time. So there's value, there's last change, rise, and rise is going to be subs init of rise, and subs init of fall, and e arrow busy equals 0. It's no longer busy, we're done, and then I'm going to say edge in var of e, which means I need edge in var, and I'm putting those at the top. As I mentioned earlier, I want people to, when they're reading the code, I want them to see the invariants for the data structure right at the top. So what are my invariants for edge? Well, value is either 0 or 1. Now, I like to write these without the E, so we're going to put in a little bit of boilerplate at the front. Assert E, and then I'm going to copy all of these into local variables so I can, oops, do that. So find the, I am famous for fiddling around trying to get Emacs keyboard macros right, because so often I can do key sequences that don't actually work, and that, of course, terminates the macro. So search for a semicolon. No. Search for a semicolon from here. Set a mark there, go back to a space, go forward 1, value equals e arrow value, end macro. And somehow that got uppercased. We're going to do that, and we're going to say value equals 0 or value equals 1. Actually, I'm not going to use my fancy assert. I'm just going to use normal assert because that's sufficient. What are we going to assert about last change? It's less or equal to tau. And rise and fall are arrays, so we are going to do subs in var of rise and subs in var of fall. Now this, I can't do this. This is a compile error. I need to do that. Rise itself is a subs, but I cannot assign an array to an array. You can assign a structure to a structure, but you can't assign an array to an array. And if I could, it's probably not something I would want to do. Well, if you want to do that, you could actually take your array, package it in a structure, and a GCC extension is to have a structure with no name. So for instance, if I had struct int foo sub 10, what GCC would do is it would, well, let's see if this compiles. Okay, ISO C99 does not support name structs and unions, and that's a pedantic error. I've turned on the pedantic errors. Even if you are running with the standard set to use GCC extensions, it still warns you about this one, okay? Because using it changes the way a lot of code works. If you use this, I can say, if I have an edge E, I can say E arrow foo. I don't have to say E arrow foo S arrow foo. It's a useful extension, but every time I use it, I have to put some boilerplate in my source code around the definition that says, hey, please turn off pedantic warnings just for this one line. Thank you. It takes a line to push the warning list, and a line to modify the warning list, and a line to pop the warning list. It's like, oh, fuck. But pedantic gets you some interesting things. So, unknown type bit. Let's get the type right. Edge.c. I did that too soon. There we go. Unused variable busy. And I'm going to assert if the invariant is going to be true, then, well, will I ever be calling edge invar while it's busy? No, I think that when I'm calling the invariant, I'm going to assert that busy is not set. So if we are busy, then we're not checking the invariance on it. And I may relax that in the future. I've been getting this feeling as we've been working with the invar routines that I may need to have an external invar and an internal. So for instance, for the heap, my external invariant may include, you can have a bubble, but it has to be at head. That would be the external invar. Or the internal invar is you might have a bubble, but it could be anywhere because we might be moving the bubble when we call the invariant check, because we want to check invariance while we're moving the bubble. So I may end up with an internal invariant and external invariant. So the internal invariant would allow some additional states to be valid during internal operations, but your externals would be what you would have when you return to a caller from outside the package. But I'm writing the external invariant here. So external invariant is values 0 or 1. Last change is not in the future. The rise and fall subs lists are valid, and we are not busy. And now if I look at it, I see that we are in fact passing edge post, which is not doing an edge yet. So edge E, edge init E, and this should create an edge and initialize it, and we notice it did not fail. What if we change the assertion? This should now fail, and indeed, assert busy failed, so we're going to put this back to where it is. So we are detecting invariant failure here in edge post. Post and bist are both going to want an edge. Bench is going to want an edge, but it still needs to init it. So those guys all get their little things. If I were paranoid, I would check the invariant here. So if edge init were considered to be a time critical function, then the invariant checks might get turned off. And at that point, our tests would want to explicitly check the invariance. So yeah, we explicitly check the invariance in the test for when we test functions that are time critical, because they don't. Edge init. So next thing is I want to allow people to subscribe to the rising and falling edge. So I'm going to add a function. Why did it not indent that? There we go. That's right. I'm not doing the formatting in my build loop anymore because it took too long. So I have to explicitly do the format over here. That's fine. I will do it when logs and bench both exceed. I will do the reformat. So anytime we are not building properly, anytime there's any error in the logs, we won't be touching the formatting, we hope. Well, let's try that. What if I say XX here? Wait for it to build, and I see the error, and it does not run indent because there's a compiler. If we ran indent on this thing, it would do all sorts of bad stuff because indent does not like code that is not syntactically correct. I could install Clang and use Clang format. It's a much more modern indenter, but 1990, we didn't have that. We had Berkeley indent. So using what we had. Classic tools, old school tools. Next thing is, I'm going to have a function called edge rise that says when the edge rises, I'm going to call step fp with arg step ap. So we're going to append a thing to the rise for that, and I'm going to do the same thing for fall. I'll just write them at the same time. And we need to have names, AE and FP and AP. You'll notice I'm not passing around steps, because if the caller had to package up a step, which is a array of one thing, array of one structure, and then it passes that, which types it in memory, and we get down to something working on a list, well, we've got a list of those things. We have to copy it into the memory owned by the list. So why? Just pass the two parameters. So these two guys are of step FP and AP. Well, void E to do register sub for rise, FP and AP. Something that I haven't been doing before now, which I need to do, is when I put in one of these things that says, ignore the fact I'm not using this parameter, I need to put a comment on it that either says to do, use it, or it says we don't actually use it, to make absolutely clear to the engineer reading the code, this is as intended. Okay. So this compiles and builds and runs with these guys no opt-out. So for power on self-test, what do I want to do? Well, I need to have a function that I can add to rise and fall. So I'm going to say static void edge riser saw rise, and I'm going to have some sort of context I can pass it. Put our static functions down at the bottom. And we need type def struct sedge ctx. I'm getting more and more boilerplate building up, which is going to be stronger and stronger motivation for why we need to invent something called C++. So what is in here? What is an edge context going to be? I want to have a counter. So my saw rise and saw fall can count when they saw it. And tau last update. So I am going to also include in my context when we last updated. Just because I want to display this stuff, as we test, I want to verify this is doing what it's supposed to be doing. So I verify the counter. We saw the right number of edges. I'm going to verify the time of the last edge, and these guys. Oh, the thing is with edge, once you register yourself on the subs, you're done. You don't need to register yourself again. So I think I'm going to include a message to print in the context. So when we get to our service functions, if we've got a message to print, we're going to print it, probably with a whole bunch of other things. And if we don't have a message, we will be silent. Okay, so there we go. Static void edge ctx init of edge ctx and cstr. Oh, come on. So CTX okay, and CTX arrow message equals MSG. So now I have a way to initialize a context structure, which gives us enough flexibility to write some tests and benchmarks. And currently this has an error because CSTR is not defined. CSTR should be supported in unknown type name C*. That should be in support.h. It's just str. Grep minus WNF. Where do I use CSTR? Str.h.c. Where do I use str? Arguably, we should be using str, not CSTR. Arguably. Well, it is a C string, not a string. Specifically a C string in that it has a null pointer and a null byte at the end. I think I'm going to name that. I'm going to rename this type. I'm going to go from stir to C stir. Because I think in some of my documentation that I wrote this morning, I called it C-stir. And of course, that's going to be an error in all of the places that use stir. There we go. Okay, so these guys, void. Well, instead of putting the void in the comments and then coming back and doing it, I will just do it here. So what we want to do is see saw rise. I see CTX arrow counter plus plus. If we have a message, I'm going to use stub to print it. So we're going to get an output on standard error that has our file name, our line number, our function name, and anything we print here. So at %LLD, so at tau, rising, have seen %D rising edges on %S. I'm going to assume message is the name of the edge, or we'll write some text that will fit in that sentence if it not. So at CTX arrow last update, have seen CTX arrow counter rising edges on CTX arrow message. Need to cast these. So that changing the data type inside the structure doesn't cause me to have to change my stub call, and CTX message will always be a proper string. Okay, so that built, and that ran, and fall is like rise. Saw edge, fall, saw edge, rise are defined but not used. Edge, CTX init is defined but not used because we haven't done it yet. So what do we want to do? For post init, I just realized if these are pointing to standard error, what I want to do is send these to standard output so that multiple runs of testing will compare them, which means I do want to identify who we are, but I don't want to put in things like file names and line numbers, which might change during the course of the build without invalidating the test. So we're going to printf in %s. No, let's say edge saw rise. Let's not count on func. So if we change the name of the function, we would have to also change it in the printf, and that would key us to remind, well, no, let's just do %s. Okay. Make it real simple. Okay, we are not going to be re-indenting because we have warnings here in our log file. No, we are re-indenting. Warnings aren't good enough to keep us from re-indenting. That's fine. It's okay because that means that even if we're not using code yet, we'll still get it re-indented. Perfectly fine. So still complaints that we're not using it. So let's set up a capture of rising and falling edge. This is for power on self-test. So we're going to do a edge CTX, rise, CTX. And we're going to duplicate this for falling, but let's get the whole thing in first. So edge rise of rise E, and this is going to call edge CTX edge saw rise of rise CTX. There we go. So, of course, this gives us warnings now because edge rise expects to see just a normal function, which takes a void star pointer. We're not passing in a void star pointer, so this needs to be a macro. So we need macros for edge rise and edge fall that cast appropriately for these guys. There we go. So the macros, the compiler will still warn us if this cast is really to an actually incompatible function. So for instance, if we want to deliver to a function that takes 3 parameters and we do this, it's going to reject it. Even with all the casting and everything, the compiler will reject it, saying this is not something that I can make compatible. But for simply a function with a different kind of pointer, this works perfectly well. So it'll catch any obvious real errors, and it will pass all of the useful ways we are ignoring what type system C has. So passing argent 1 of edge init from, okay, so edge init, edge CTX init. There we go. This is why I don't use this kind of cast function everywhere, and it's why I don't cast the things that I want to have checked. So too few functions to edge CTX init because it wants the message. So it's going to say %s, function name, the tau, the count, and some sort of a message. Post on. If I was really fancy, I would set this up with var args and everything, but I'm not that fancy. Post edge. There we have it. So we don't have any output yet. So I can, in fact, put in some assertions here to test that establishing this, calling edge rise and edge fall, should not change the state of edge E. So I can do assert E arrow to 0 equals E underscore. Actually, how about if we go ahead and use assert EQ int, E arrow value. I want to assert that the last change is less than tau. I may need to add LT integer to my test list, but that's what I want to do. And in fact, I do. I need to build that. So down here where we have assert EQ integer, I now want to assert LT integer. And I want to reverse these because I want my expression to look kind of like what I'm doing here. So let's fix that up here too. It doesn't make it important on the equality. Order, comparison failed. Expected value is less than that. And this is equal to that. So E has nothing called last update. What did I call it? I called it last change. Oh, didn't want to change it in CTX. CTX is really an update call, but I do need this to be last change. Wait for that to compile. There we go. No failure, and I am not doing anything yet, so no messages. What else do I want to assert? Well, we would like to reassert our invariance also. Could do that before these guys. So assert, so edge, invar of E. I am not in my test going to assume these guys call, so I'm changing what I said earlier. So edge init, I'm going to call invar when it returns because I'm not going to assume that init calls it. Bench will assume everything is okay. It's not going to demand invariance, but everywhere else we're going to go ahead and do that. So we're going to do invar checks at the end of rise and fall. We're going to test the equality and that. And is there anything else we want to check beyond the invariance? It'd be nice to be able to assert that rise and fall are not empty. So do I have something in subs that gives me back whether it's empty or not? Other than looking inside the structure, there's nothing in particular, so I'm going to look inside the structure. I'm going to assert that I also want to assert invar checks that that's stable, so now we just say assert GT integer of 0, E arrow rise, arrow len. And E fall. So the power on self-test is a white box test. We are doing a test of edge that references its internals. White box versus black box, again, it's a distinction I will not generally make on tests, but I'm going to point out that this is a white box test. A pure black box test would test it without doing only using the public interface. And it's often that you'll produce black box tests which also form, here's an example of how to use it, whereas your white box tests that reach inside and muck with the state are bad examples. So because I'm looking at rise len and fall len, this is now a bad example of how to talk to edge. But we now have a compile error because we don't have assert GT. That's easy. So now I'm getting a pattern here. I'm going to say assert op integer, and I'm going to have op be a macro. Observed. Like that. Comparison failed. And we are going to say, we're going to put the op in here. And I'm going to put it in 2 characters. So those should align. And comparison failed, and this is going to have comma pound op here. Like that. Now all these macros can be written in terms of assert. I think. Before I rewrite everything else, let's see what that does to us. How about that? So now, because we aren't actually doing the right thing yet, assert GT, assert GT is still asserting less than. Okay, so we're good. So we need less than integer and greater than integer. And as long as I am doing it, let's do LE and GE. So this symbol I'm getting here for greater than or equal to, this is a ligature. In typography, if you have pairs of letters that when they appear together on the printed page, you want to do something to make them fancier. For instance, one might, if you're, anyway, it's a typography thing. You have, like if you have FF being printed in a book, you might take the 2 F's and move them closer to each other. And if you're actually typesetting with actual physical slugs of lead, you might have a special slug that has 2 F's on it that are moved together so they kind of overlap a little bit. And it looks better. It's called a ligature. So ligature support in text on a computer is saying, well, I see a less than or an equals sign, and I have a special entry in my font table that says, instead of doing a less than followed by an equals, I'm going to put a less than or equals that takes up 2 spaces wide. So it's still the same right width, but it does this. And we've got ligatures going for all sorts of things. I can even do that and so on. Anyway, I turned on ligature support in Emacs, and I've decided I like it, so I'm keeping it. But that means that in my source code, when you look at it on my screen in my editor, you're going to see this less than or equal to sign, and it's going to take up 2 code places. So for instance, we cannot write a less than or equal like that. However, there are multi-byte. Okay, so this is the Unicode less than or equal to character, which you cannot use as a less than or equal to operator in C because C doesn't do that. I cannot define a Unicode character to be an operator. So that's why you'll see this and you won't see the other one. So we do that, and now I have all of these things. So assert GT is greater than, and so on. And now we have some test failures. This says, after doing edge rise, I am asserting that rise len is greater than 0. And it's not, because guess what? I haven't written edge rise yet. So in order to satisfy this test condition that is failing, oh no, I'm doing test-driven development. Oh no. Yeah, this is the kind of step in a procedure. People will look at this and say, oh, let's build an entire develop methodology on this idea of write a test that fails, then make it succeed, and you're done, and then refine it afterwards. Sometimes you do that. I don't do it all the time. Well, what do we want to do for edge rise? Well, we want to add the function and the argument pointer to edge. Let's take a look at the subs.h. I'm going to use the public API for doing an add, which is subs underscore add, and I want to pass in the subs list, which is e arrow rise, and the FP and the AP. We're doing the same thing for fall. Okay, there we go. And it runs, and it has no failures. Edge rise and edge fall are not time critical. This method, this function is not time critical, used in any time critical path. So having that comment there means that if I do find that edge rise is in a time critical path, then I know as I'm going through optimizing and I'm going through a profile and I'm at a time critical path and I hit edge rise and oh goodness. Well, first of all, I don't really want to call it edge rise because we are not setting the edge, we're not setting the edge high. And if I see edge rising code, it might be, so we're going to say edge on rise, edge on fall, and change the macros. So this is not good English, but having the package out on the left like this helps me deal with the fact that C doesn't have namespaces. In C++, this would be edge : on rise. Arguably not any better. But you can elide the namespace in certain conditions, but we cannot elide edge underscore unless you'd say pound define on rise to edge on rise. Do that sometime in the future if we ever need to, and if it helps clarity. Until then, we'll just use edge on rise and edge on fall. So edge on rise, warning, implicit definition of function edge rise. Apparently, I didn't get everything built together, did I? Yeah, okay, there we go. Saw on is there we go. Less obscure. If I put func up on that line, will my indenter leave it there for me? Yes, it does. Good. So we still haven't actually triggered any of these, but now we are actually seeing that there's something on the rising list and something on the falling list. So, now we want to put in something where I can actually ask for a high or a low. So that's going to be simple extern void edge high and edge low. This says I want edge to be high and I want edge to be low. And if there's a rising edge or a falling edge, do the right thing in the background. We're done. Now I'm actually going to put these before, oh no, I will leave them where they are, never mind. Edge saw rise, edge saw fall, these are test functions. We're going to scroll up here to the implementation, init, on rise, on fall. We're going to grab those external declarations and put them in here. This function is a time critical function. I anticipate that within this simulation, one of our time critical paths will say, I want to raise this edge. I want to lower this edge. So first of all, if E arrow value return. If we're not changing the value of the edge, we're done. I'm going to even allow this if the edge is busy. So if I set it high and I go through a chain of things doing stuff and it comes back and wants to set it high, we're done. Don't recurse, don't service, we're done. We've got nothing to do. Okay, so now we know that we're going to be changing the value of edge. We want to assert E arrow busy equals 0. Actually, I'm just saying not E busy. Whether we're going high or low, if we're changing the value, if we're busy, we're done. We're going to set it, and we're going to clear it before we return. Actually, I'm going to derive low from high shortly. No, because everything's going to be first in the internals. Busy is handled the same. E arrow value equals 1. And E value is going to be 0 down here. And now we want to do a subs run of E arrow rise here, and a subs run of E arrow fall. Whoops. Down here. I think it's run, is it run or run all? It is run. So I don't have a subs run 1 because it would just run the first sub and we would never get the second sub. So run 1, run 1, run 1, and we'd run the first one over and over again. So run just runs all of them. So this says, raising the edge, we say if we're doing nothing, we're doing nothing. Assert we're not busy, set the value, run the edge, clear busy, and we're done. High and low. Okay, so we are ready to do that. The other thing, oh, I almost forgot. Go back to look at our state. We forgot to update last change. Assert E arrow last change is less than tau. And then we're going to say E arrow last change equals tau. So there's our, so this, I'm going to comment this, protect versus infinite recursion, early out if no state change. Having comments like this for why I'm doing something is probably a good idea. This class is simple enough we are unlikely to need the comment to tell us, but it's not bad anyway to have it. Also means I can grep for the word protect or recursion. Detect hazard. There we go. And we re-indent, and indent is kind of clever about where it wants to put its trailing comments. It will put it at an appropriate distance to the right, and it will try to line them up, and longer comments are getting put in earlier. That's okay. This looks fairly good. And this is indeed a guard. I'm going to put in some white space here to make it even less readable than before. Not busy, go to busy 1. Notice as I put in the white space, I noticed that this wasn't doing the set busy immediately after the test. If I were trying to do this in a multi-threaded environment, then this test and set on busy would be an atomic lock of some sort. Arguably, if one thread is changing an edge and another thread tries to change an edge at the same time, that's a hazard. So arguably, busy would not be a mutex, it would be a test and set, and fail if the old fail if it would still do an assert, but it would use an assert that's an atomic. So we'd do a swap, we'd swap a 1 in, and if the value we got back wasn't 0, we would fail. But currently, the simulation is not multi-threaded. Someday, if things get big, may go multi-threaded. I am running this on a modern Ryzen CPU that can handle a lot of threads. And by handle, I mean run them literally in parallel, not time slicing, but literally have different cores running them, and a lot of them. It's the, hold on. What is view processor information? This is a 5950X, so it's a 16-core processor. So the reason why I went with that particular processor was I wanted more cores. It's not the best processor for playing games, and it wasn't when it came out. Okay, it was more along the lines of you are a software developer that's doing a lot of things that use a lot of cores. So one core. Necessarily, we're not going to have one core running faster than any other CPU, but we'll have a lot of cores that in aggregate are doing better. So that's what I've got inside the machine, because I anticipated building things that were doing a lot of cores. I've actually messed around with that. It's pretty cool. I have some multi-thread demonstration code from decades ago that just eats that stuff up like crazy. I wonder if I may polish it up and show it off. I may not, but it's kind of cranky code. Yeah. Sometimes it doesn't run, you know. So here we are. We have time critical edge high, time critical edge low. By time critical, this means we will be benchmarking them and saying, if I go high, low, high, low, high, low, high, low over and over again, then my time to service an edge high when I have 1 subscriber or 2 subscribers or 10 subscribers, we're going to characterize that and benchmark it. But the benchmark will necessarily have, actually what I'll probably do is benchmark it with only subscribers on the high edge, because most things we're not going to be having subscribers on both high and low. Some things will be mostly high, some things will be mostly low, a few things will be both. If nobody ever subscribes to either one, then why are you using an edge? So back down to this. So for my test sequence, I need to do some edges, and I cannot test that I'm doing an assertion failure, because that would, would be an assertion failure. So these things where I am doing an assert not busy, I can't test that that's going to catch it. I will have to test that manually and say, oh, I did something wrong, and it caught it, and it did that. And then at that point, I will put a comment in that says, yes, this works. And that's called testing by certification by the engineer that it works. It's the weakest form of testing. So all these things, I cannot test paths that we will do an assertion failure on things, but I can test things that work properly. Actually, what I can do is I will go ahead and set these up without anything special. I will say edge high of E, edge low of E. Actually, what I'm going to do is do an edge low. We're start low. Edge low should do nothing. edge high should do a delivery, another edge high should do nothing, edge low should do a delivery, another edge low should do nothing. So we're going to verify that the edge low and edge high are idempotent. For power on self-test, what do we want to do? Let's do a high and a low to verify we deliver. Another low to verify idempotence. Two highs, so deliver and idempotent. Let's do 3 of them there. So there is the sequence that I want to run through for power on self-test. And obviously we are going to have to insert all of our state checks, and we're going to have to insert proper advancement of tau. We see already we have an assertion there that last change tau has failed on an edge low call. We didn't get a traceback up here because I don't do those, but I know very well where that is. So we're starting out in the low state, but our last change was in the past. So edge high is fine. And edge low, we need to tau plus plus before doing edge low. What I'm going to do is I'm actually going to advance tau before each one of these calls. Wait for the test to complete, and there we go. And I am seeing some output, and I didn't put a new line at the end. My macros that put the file name and line number and so on also add a new line at the end, and I just need to make sure to do that manually. So this says that I will do the following. So the difference, it's doing the difference, and then it's, I think I am printing the file without printing the name of the file when I print it. Let's check. You make file, make comparison, says BIST into standard error, difference does a check into difference. I can actually have make print what it's doing. So it says bin logs, fix C headers. Oh, okay, so this is the call to bench itself. So bench calls post because it's calling post, and post is currently printing output, which I do not want to do generally in post. So what we're going to do for this is post will be silent, BIST will not. So BIST is a copy of post. We're going to go back here to post, and I'm going to go in here, and I'm going to set the message pointer to null. Okay, there. So this says when I'm running bench, we're silent. When I'm running BIST, we're outputting the stuff. Post is just doing it, but it doesn't have any tests in here, so we need to actually verify. So for each one of these calls, I need to write power on self-test code that checks the state of edge afterwards. And here's why here's where I would normally hit the button that says the recording should run at 4x normal speed because I'm going to be doing a lot of typing, but I don't have that. So assert. So when we do it edge high, I'm going to assert that 1 is equal to value and tau is equal to this. We go low. We go low again, and I'm going to assert that the last change is LT tau. We go high, and it's EQ tau, EQ1. Actually, let's do all of the value equalities here. And let's do all of the taus for where it sets. So we're high, we're high, we're high. We go low, we go low, we go low, and less than. If I've done that right, we should pass. We do pass. Down below, we are printing things. And the tau value is going to change from run to run. So I can't really print tau raw here, but what I can do is print tau minus a t0. So let's put a t0 in our context. I will call this update delta. So change the name because I'm changing the semantics of it. And now, of course, we're going to have compile errors. Init, we're going to say ctx arrow init. Oops, what did I call it again? Tau is equal to tau, and the initialized update delta equals 0. So all these places that say last update equals tau needs to instead say update delta is equal to tau minus ctx init tau. Oh, only two places. So all that jiggery pokery I did in Emacs just then to change it everywhere was overkill. So in printing out, this needs to be update delta come on, I want a uppercase delta and lowercase tau. This is where I expect my entire audience to be able to recognize Greek characters. Tau is easy. Delta, you need to know. If you don't know that this triangle symbol is uppercase delta, well, you know it now. Has no symbol called update minus delta. There we go. So edge saw rise at 0 delta tau, 1 count on post edge, at 1 delta tau, 1 count, at 3 delta t rise, second the rise, and 6 delta t, the second rise. So this is actually something I can print to the text file that logs what happened. And we can do a comparison on this. And from run to run, we'll see that it didn't change from run to run, which means that if I change the way things work, I can look at the change in the output, and I can say this is okay, and I can accept it without writing a whole bunch of test code. However, post will forever need to have all of this because power on self-test needs to be absolutely silent and fast. So is this the minimum I want to do for power on self-test? I believe so, because this verifies that rising and falling edges are delivered, and it verifies that the thing is idempotent, and that the last change is updated when last change is only updated when there's actually a rising and falling edge. This is not the minimal set of things. I actually am running one extra, which I can get rid of. So the minimum to actually check all that is, we are low. Let's do a low precondition for the test is that last change is less than tau and value is 0. And we're going to do a edge low of E initially, which is going to be idempotent. Then we're going to do an edge high that changes it. Now, if I didn't do this, this should cause it to fail. Interesting, I did see a failure on the right, and that there's a log difference. Oh, I saw failure in the log difference. So why did this not fail here? I did an edge low and edge high without changing tau. Oh, right, edge low did not change the state. So is it true that I want to update last change? Yeah, let's change it from last change. So if somebody calls edge low, and then somebody else calls edge high at the last time, that's a hazard. Okay, so this is not called last change anymore. This is called when. I'll just call this when. So whenever anybody calls edge rise, or edge high or edge low, when is going to be set. Change the semantics, change the name. This also means that we need to do something at the bottom. So we need to update when, whether we're doing all this or not, but I still want it to be very, very fast if we are not changing the value. So if we're not saying, okay, if we call edge high, edge high, edge high, edge high, we're going to be okay. It's so we only want to do the assert if the thing changes, but we do want to update the when if it doesn't change. So I would like to write this as a condition like this. Do real work if state changes. And the when updates out here. Register include register remember tau from every time someone specifies the value, even if the value does not change. There. So you do that. Additionally, I really only need busy to be set during the subs run here. Can I bubble all of my assertions up to the top? Yes, I can. I can do assert when, dust, and tau, and assert not busy, and run it. I need to set value before going into subs run. Let's set busy after we test it. So this is the order. There we go. And now I am getting the desired effect here, where if we were low and we force low, then when, okay, so when is always going to be equal to tau. There. So edge in var, here it is less than because we have initialized it. Okay, there we go. And I'm going to assert its value is initialized to 0. Anything else I want to assert about initial value? When we're going to assert that rise and fall are empty. And we are going to assert that when we get here, we are not busy. Yes, I know that's tested by invar, but in case we decide that the invariant will pass when we're busy, I'm going to test it here as well. So all of that is correct. We register ourselves for a rising edge. Is there anything else there we want to check and make sure that registration of the rising edge has not changed? Not really. Well, just in case, I am going to toss those in. It would be bad if registering someone for seeing a rising edge caused a rising edge. Okay, so come down here. We have already asserted these guys. There we go. So we do the low. We say assert that 0 is the value and tau is the when. The edge itself doesn't remember when it changed. It remembered when it was set. Much simpler. So for the purposes of this test, the only difference between idempotent changes and actual changes is going to be whether we made the call or not. Now currently this should have a failure in this edge high because tau changed. And indeed, oops. It's too bad I don't know the calling point here, but I do know the calling point because I'm the engineer that wrote it. It's this guy right here. Edge condition failed here. So edge bist is going to do the same thing as edge post. The difference will be the edge bist will actually be chatty about it. Now let's actually compare bodies, and I will look at the actual differences. I'm using an Emacs command, Emacs key that is bound to step forward to the next difference, and if you're at the difference, step across it and highlight it. So we did not pick up this stuff yet. And it compares the current window with the previous window. So we are turning on a message, and we have some assertions that we added here. Turning on a message. add some assertions, and that's it. So BIST is just like POST now. We may extend BIST later in that it does exactly the same thing. The difference is it has those print lines. And currently we are passing all the things except we are printing something to the log that is not yet in the log that we accept as true. And what we are printing is 1 delta t, 1 count on post edge, 2 delta t, 1 count on post edge for fall, 3 delta t, second time we saw a rise, and 6 delta t, second time we saw a fall. That is correct. That's the pattern I put in. So now we can go into log, and I can remove the expected. And when we trigger another build, it will set the expected. This is the TOFU model of testing. TOFU is trust on first use. It's a term I learned in the security arena. Trust on first use is like if you're going to do a secure shell to a remote host. The first time you connect to the remote host, you receive back the host credentials that say who it is. And normally, if you're not using a squishy TOFU model of security, you get that host key back and you compare it with a known value of the host key from a known source. So for instance, I would visit a site and I would say, okay, I need your public key for your host. And they would give me the public key and we would go over the checksum of it. And I would verify that I have the actual public key for the actual host, or I would receive it through a trust thing. Then later on, the first time I SSH'd out to the host, it would say, what's your public key? You would send that back to me. I would compare it and say, yes, I've got it. TOFU says, I SSH into your computer hands me back the keys. I presume there's no man in the middle, that I am getting the key correctly, and I trust it. So TOFU, trust on first use. So how that applies here, this is a built-in self-test, which is printing out a bunch of text. And by deleting the file and allowing it to run, I am trusting that the first output I receive from BIST is correct. So TOFU. And I'm going to cook the TOFU by looking at the file and saying, is this correct? And as an engineer, I can stare at this and I can, as an engineer, cook this TOFU and say, yeah, this is good. So I trust this file and I'm going to check it in to Git. And now we do our make. And make comes back with, oh, we're passing. Good. Now if I trigger another build over here, I look over at my other window and it runs the build and it comes up completely perfectly clean in that window and we come up completely perfectly clean in this window. So we now have Edge passing its power on self-test, passing its built-in self-test, which verifies the things I want to verify. We are only placing, I think we're only putting one thing on it. So let's extend BIST. So BIST is going to put, say, 50 consumers on each of these guys. So what I want is const int subscriber sub count is 50. And then this is going to be the same, so fall like that. And now we need to initialize all 50 of those guys. This is rise CTX sub. So this is an array of arrays of structures. So rise CTX sub 1 is an array of one structure. So this is still semantically correct. But we will have a compile error on the second one. Anywhere we use rise CTX or fall CTX without using the subscriber count is going to have that error. So we're going to go down here and we're going to change rise to fall. Okay. So this now says when we set up 50 subscribers, each with its own context, like this, when it's done, we're going to verify the edge invariant is still there and all these are there. And instead of saying greater than 0, I'm going to make this stronger. I'm going to say EQ 50. And that tells me that I also need to go up here, and I am going to say that these are EQ1. Now, I used 50 down here, but I need to make it subcount. So now that BIST has 50 subscribers, you know what's going to happen? We are going to see all of these guys. Now, in the real world, if we've got 50 different subscribers, they've got their own names, and they will be putting their own names out here in the init call. So what I'm going to do here is I'm going to format a string. So instead of on post edge, this is going to be in subscriber %d. Rise subscriber %d. There we go. Now format will allocate a string and format things into it, and we're going to store that string inside the edge CTX. And we don't actually destruct any of this stuff. So if you're running BIST, this is allocated memory that's not going to be freed. So if we were running with a debug allocator that told us about things we allocated and didn't free, this would be a problem. Just in case I do that in the future, I am going to write a edge CTX detour. Actually, let's call it free. The use of the word destructor came in along with C++ in my experience. It probably existed before that, but that's where I first saw it. So the free is going to take the edge CTX, now free isn't going to free the edge itself because I didn't malloc the edge. We're being passed in a pointer to an array of 1, but we need to free the stuff that's inside it, specifically message. I think it is slightly safer to clear the field before freeing the memory. So there we go. And now we just need to edge CTX free everything we did in edge CTX init on. And yes, I'm going to do it even on these where we didn't actually allocate anything. C++ addresses this by having RAII. So literally, as we went out of scope, if we had a object of type rise CTX on our stack, as we went out of scope, it would call the destructor, and that would happen. And it would happen in a reverse order like that. So we're just going to do this. But this needs to be the loop. hold on. Aha. Edge free, fall context is free, rise context. There we go. I'm going to maintain the RAII ordering here, so we're going to go from the top down on these guys. It'd be sub minus minus. So that means that if we did use a debug malloc, where at the termination of the program, it reports to you anything you allocated you didn't free. If we do decide to do that, it means that at least in this case, this BIST will not be triggering it. It is likely that we'll have a large number of things in the simulation that we malloc that are then noted as being immortal and never deleted. And if we do that regularly, it means that our debug malloc is going to complain about those things, at which point we either need to revisit whether we do it or not, whether we use debug malloc or not, or if we just do it, use debug malloc, and keep track of all of the immortal things so we can remove them from the list when we look at it. But at least this is one thing that isn't going to get put on. So MSG, message is actually a const char star, which you don't pass to MSG. So we need to cast this to a char star to let it know that, yes, this is actually, we're now modifiable memory because we want free to be able to scrub it. And that compiles and builds, and it changes our output so that we say see rise. The subscriber list are strictly in order, so having the subscriber number in the test output is useful. We actually see that these are happening in order. And that is correct. Let's verify it by looking at the log. So these are getting bigger. So at 1 delta T, we have count 1 in all 50 subscribers. At 2 delta T, we have 1 count in all 50 false subscribers. Then at 3 delta T, we have 2 count, second count in rise subscribers, and second count in false subscribers, and that's the end of it. So this is correct. So let's cook the tofu. Expected goes away. And trigger a build. And we're clean. Now, I did put in a flag inside the formatting. Oh, I've got Q in front. There we go. There we go. Okay, so that's nice and clean. And we are testing our edge with 50 subscribers. Now that forces us, what we can say about 50 subscribers is that either the subscriber list starts out with a capacity of over 50, or it expands it as needed, and we still get the 50. 50 subscribers on Edge is a good number. We may go higher. This does not prove that our increase the size of the list is working, prove unquote. However, as an engineer, I can tell you that the code itself to do the expansion is not complicated enough for this to succeed going up to 50 and to fail further than that unless somebody started out by initializing it to over 50. So the evidence provided here for the thing being working, combined with the knowledge of how it works, comes together to again have a semi-relies on the engineer proof that we're working. So I will accept this as a good built-in self-test. So now we want a benchmark. I am going to take this entire function, edge bist, and I call it bench edge. Okay, static void. So this is the function we're going to call, and it's going to take in a edge E because I need it to take in something. And this is going to be a benchmark that does a bunch of tests. And it's not going to knit and invar the edge. We are already going to have initialized. Let's do all of the initialization stuff up front. So like that. We're actually going to call that from our benchmarking thing eventually. So coming in, we're going to take away all of the asserts. Now, what do we want to do? What we really want to do is tau plus plus edge low, tau plus plus edge high. That's all we really want to do. And when the benchmarking is done, we're going to free the contexts. So each iteration through bench edge is going to run the, let's do rise and then fall. So we're going to run a rising edge and a falling edge, and that's bench edge. And our benchmarker will run that over and over again and will tell us how many times that works. But for now, I'm going to just run it once. And we're going to say edge in var of E at the bottom and at the top like that. No. There we go. So we're in benchmarking, which means I want to have no message. Okay, that's clean. So we can run bench edge once without failing. So now I want to grab my benchmarking from somewhere. This should be static, shouldn't it? No, it shouldn't. Sorry. This is our key thing right here. Double dt is equal to RTC elapsed of bench edge E. And we are going to have a print that says ns per edge iter. Now I want to run this for various numbers of subs. Do I? No, let's just run it for 50. The amortized cost per call, because I'm just doing a linear scan, we can look at subs for how subs handles more and more. This will be edge given as subs at 50 jobs. So we'll look at the bench subs jobs 50 line here on our output. That's subs iter. Actually, subs iter, we don't even break it out by length. We just say it's there. Longer lists, it's still the same cost for each call. So we'll just do 50. So ns per edge iter, and there's going to be a bench end and a bench val of dt. And this is actually dt divided by 100, divided by sub count times 2, because we have each call that RTC, so RTC elapsed calls bench edge, which makes 50 rising edges and 50 falling edge surfaces. So this says that when we are servicing the edges, with all of the things we're doing around working with an edge, this amortizes out at 50 guys to 2.8 nanoseconds per subscriber. And that compares with subs of 1.3, so there is still some overhead in what we're doing. Significant overhead. Well, what are we doing in edge high and edge low? Let's go review them, and let's think about what we need to do here to make it faster. I am going to make a macro called, well, let's see, what are we doing here that's optional? Pound define edge hazard detect. I'm going to put these in here, so we're going to configure our edge system to do things or not do things. So if edge hazard detect is set, we'll have when. So I like to put the optional things at the end and in an order where we will tend to, if there's several independent options, where we tend to have the earlier ones turned on when we have the later ones turned on. So edge hazard detect is probably our more complicated thing, so we'll make that that way. Now if I undef, so this will note all of our taus. So we want to be able to turn off hazard detection because that's going to be expensive for us. This says no semicolon at end of struct or union. Because I deleted the semicolon here. Got it. Silly me. So we need to macroize a whole bunch of things. Okay, so assert when is equal to tau. When is at the bottom, so we're going to move that down in general. So the hazard detection encompasses well, that much of it. This is also something that you did a lot of, probably still do a lot of. Which is making some code optional depending on compiler options. So now, wherever I mention E arrow when, I'm going to comment out the line with that macro. So search for E arrow when. We're going to do that, and that's the macro. And that now runs. interestingly enough, there we go, 2.3, 2.3. We're still doing a bunch of things. So the next thing is the recursion check against busy. So I'm normally going to do the recursion check, but I can turn it off. That means that we still want to, so we have a recursion detect. And that protects busy. I'm going to go straight to setting up the macro with a keyboard macro here. So we're going to search for E arrow busy, yoink that, and do that, and we're done. But now I need to actually watch this because we may be, yeah, like this. There, there. Okay, assert not busy. So anywhere I have the word busy that wasn't E arrow busy, we still need to do this. I think mostly I just work with it in place. And in the interest of, I'll do that. And when there we go. So that encapsulates our recursion and hazard detection, so we can turn them off. Forcing a build. So with all that, we're still running 2.3 nanoseconds per call, which means that these guys aren't actually costing us. Interesting that these turn out to be essentially free relative to everything else. Well, 2.3, so half a nanosecond is what it's costing us to do recursion detection and hazard detection. Interesting. So that's about, we give up about 10% of our performance to do this. I actually like doing things that get me 10% extra performance, but we're going to leave these on. Turn both of these off for about, to reduce the edge overhead by about 10% when there are 50 clients per edge. So the other thing I want to do is I'll do the same test with fewer clients. The overhead I'm manipulating is on a per call into edge, not a per call into the client. So if there are fewer clients, that's going to be that same cost amortized over fewer clients. So if subcount is only 5, we're running 5 nanoseconds per. Versus 5 without checking is 2.7. So with only 5 guys, this is costing us a significant amount of change. So this costs us significantly. It does amortize out as you get fewer and fewer subs, or you get more and more subs. So for sub count of 1, with nothing going, our cost is 3.6 to get an edge delivered to one subscriber on the rising edge and one subscriber on the falling edge. And that goes 3.8. So it's not a huge cost, and it's cost per edge high and per edge low that changes. It's cost per actual transition. I'm going to make a judgment call here that this is perfectly okay to have turned on all the time. So we are just going to accept that as our time. Later on, if we get deeply, deeply into optimization, we will revisit this and figure out what we want to do and where we want to do it. But until then, we're just going to deal with it. I do want to run BIST, run BIST with 50 because we need to check that that works. I'm going to run bench with 5. No, let's run bench with 1. Because running with a 1 is going to give us a better notion of what's going on. In fact, let's run. Do I want to run with 1 in the rise and none in the fall? I think so. I think I want to try it with only the rising edge going. So if we have an edge and it's only got 1 subscriber, so yeah. Oh, right, and because I don't have, okay. So we do not divide out this time, so sub account is just here. So really what we have is rise subs, and separately we have so what can I do to make this work? With fall subs set to 0, I'm not sure what will happen when I declare an array of 0. ISO-C forbids 0 size array, so I'm going to declare my array to be 1 bigger, just in case. So that says, if I only have 1 guy subscribing on 1 edge and we are updating it over and over and over again, then our cost for that is 5.6 nanoseconds per edge. Okay. So that's kind of the bedrock. We may optimize that later. We may come through and rip up a whole bunch of things and make edge basically run fast and loose, basically a dragster with no safety equipment. But that comes later if we decide that it's worthwhile. And I believe that that is everything we need for Edge. For those of you that are thinking, wow, that's a pretty simple little class. Why did it take you 2.5 hours to build it? My gosh, I could have written that code in an hour and debugged it, or I could have written it in C++ in 30 seconds. Well, yeah, you could have. And back in the day, I would have turned out something like this probably in about 10 minutes. I wouldn't have done all the testing. I would not have done the benchmarking. I would have written the code to be fast and loose. I would have written it to do its job quickly and quietly. I would have tested a couple of cases manually, and I would have gone on to the next thing. Like I said, something like this would be about a 10-minute job. But I am trying to run through the same process that I would use for larger modules to show what that process was and to exercise it. So to basically document what old school coding really means. And to show when you get to writing modules that do all these things, why you would want to go with a higher level, why you'd want to raise the level of your language from what we do in C to C++ or what those are. It provides the idea of the motivation behind why it was invented. And right now the motivation isn't huge. Edge, for instance, would not want to inherit from something. Some of these might. For instance, step app might inherit from step, and so on. But as we get into larger modules, it will become more clear what some of the stronger motivations are for a language with classes, with inheritance, with exceptions, with a constructor and a destructor that are called in predictable patterns, the destructor being called when you go out of scope, for instance. So yeah, I am spending a lot more time on this than I would have if I was being paid to just produce the Edge class. But there we go, and that's working, and it's pretty good. And I need to add a whole bunch of comments to it and tidy it up a bit, but I do that off stream. What I've got now, I'm going to check in and send up to GitHub. So git status. We are going to check this really quick. Git diff-wu into cat, so we do not get fancy fonts. I added a sleep to build wait, which I'm going to take out because I don't like waiting, and I don't think I have a real problem with file save hazards. Okay, so that's taken out. We're going to do this again. Let me trigger a build to make sure that this didn't break anything. Yep, we're good. Where did my shell go? There it is. So this is our diff. Basically, I have decided to no longer do anything inside the external loop other than make loop. So in my little off-screen terminal that is running the build over and over again as necessary, I'm not seeing the logs of the benchmarking. It's not formatting. I'm just doing it. I have added I've added structure tags to my structures. I have updated my expected results. Edge got added to main. Structure tags. Stir became cstir. And we added some assertion macros. So instead of doing this from the, well, I can do these from the shell. Yeah, okay, let's just do it from here. I will have to type carefully. So we're going to do git add dot, git commit dash m, add edge. It's going to be my main message here. Also. So alsos are refine, build, scripting, do less, add structure tag to all structs, better debug, update expected output from BIST. Oh, and I'm not going to be able to edit this. Yeah, okay, nothing's going to go above the L. Everything else is also fine. Adding BIST includes attaching it to main. Structure tags. Rename stir to C stir. It is a C string. We all know what that means. It means it's got a null pointer, a null byte at the end. Document C stir. Add assert op integer for ops equal, less than, greater than, less or equal to, greater than equal to. And that's it. So now we can close the quote and let the shell do it. And I'm going to say git push. All done. So what I just did live is now on GitHub at farsight/livecoding.git, which is linked in the description of the video. The next delta on that particular repository is going to be the cleanup, where I add all the comments that I didn't write on the edge thing. So I will see you guys in the next one. Bye.